Hello, everyone. Welcome to this video on learning mathematics through concepts and examples. Today, we are going to discuss numerical integration using Riemann sum with a couple of examples. So here is our first example. The following table shows the left Riemann sum denoted by L sub n and right Riemann sum denoted by R sub n for the function f of x equal to e to the power x squared on the interval 0 through 1. So these values are given here. You can see left Riemann sum are here, right Riemann sum are here, and then for different value of n equal to 5, n equal to 10, n equal to 50, n equal to 100, and n equal to 200. So we are asked to use it to estimate the value of the definite integral from 0 through 1 of that function, and we are asked to round our answer to 4 decimal places. We know that left Riemann sum and right Riemann sum gives the estimation of the definite integral for a higher value of n. But we have also learned that the midpoint Riemann sum will be the better. And midpoint Riemann sum is the average of the left Riemann sum and right Riemann sum. So what we can do here is, to estimate the value of this definite integral, let me write here. So the definite integral 0 up to 1 of the function with respect to x is approximately equal to, because Riemann sum will give approximation, and approximation is better if we have the midpoint Riemann sum with higher n. So n equal to 5, n equal to 10, they will not give you the better estimation. If we go to n equal to 200, higher n will give better estimation. So these are already better estimation, but if we want to, get the best out of it, what we can do is we can take the average of this. That will be the midpoint Riemann sum. So what I mean by that is I can find left Riemann sum with 200, right Riemann sum with n equal to 200. We can add them and divide by 2. We can find the average. So that will be the best estimation, which is equal to, so the left Riemann sum with n equal to 200 is this one, which is 1.45837, then plus the right Riemann sum with n equal to 200 is this one, which is 1.466959, and we divide that by 2. So if you add these, if you add these two and divide by 2 and round your answer to 4 decimal places, you can use your calculator to simplify this. You should get 1.4627. So that is the value of the approximate value, I would say, approximate value of this definite integral from 0 up to 1 of that function. So we can use the Riemann sum to estimate the value of the definite integral. But remember, when n goes higher and higher, the value of the definite integral will be more and more accurate. Okay, so if we want the exact result, what we want to do is we want to have this n goes to infinity for the Riemann sum. That means if you take the limit of the Riemann sum, you'll get the exact answer. And that's what we are going to do in next example. Here is that example. Evaluate the definite integral from 0 up to 1 of the function 2x with respect to x by first writing it as the limit of the right Riemann sum and then calculating the limit. So first we want to find the right Riemann sum, and then we want to take the limit, so that would be the value of the definite integral, because the limit of the Riemann sum is the value of the definite integral. So in order to do that, what we do first is we want to find the width of the interval delta x. And you know that delta x is b minus a divided by n. So in this case, 1 minus 0, which is 1 over n. N goes to infinity. N is really, really large. So after we get delta x, next thing we want to find is xk. And you know that xk is a plus k times delta x for right Riemann sum. Value of a is 0, so this is 0. And then k is just k multiplied by delta x is 1 over n. So k times 1 over n, that is equal to k over n. So that is that is xk. Next, we need f of xk. F of xk is the value of the function at xk, which is k over n. So we plug in k over n into this function. So this will be 2 times the value of x will be k over n. So 2k over n. 2k over n. So with this, we have everything ready to find the right Riemann sum. So now let's find the Riemann sum. Now the Riemann sum will be, it is the summation k equal to 1 through n, f of xk times delta x. So f of xk is this one, which is 2k over n multiplied by delta x, which is 1 over n. So we have to find this sum. So in order to evaluate this sum, k changes from 1 up to n. So the only thing that is changing is k. So these 2 and then n, they are constant, so I can pull them out. So that will be 2 over n squared, and then we have sum of k equal to 1 through n of that k. And sum of k means sum of first n natural numbers, which is given by this formula. Let me write here, 2 over n multiplied to n times n plus 1 divided by 2. So we use the formula, and we are almost there with our Riemann sum. So our Riemann sum is equal to, what we get here is, so this is n squared, by the way, that is n squared. So when you divide this, you'll have n in the denominator, 2 and 2 cancel. So we get n plus 1 divided by n. So we get n plus 1 divided by n. Or you can also write this as, let me simplify a little bit. So the Riemann sum is equal to, okay, n divided by n is 1, then plus 1 over n. So that is the Riemann sum. Now, if we take the limit of the Riemann sum, we get the value of the definite integral. So we say, hence the value of the definite integral from 0 up to 1 of that function 2x with respect to x is the limit of the Riemann sum. I can write it like this, limit as n approaches to infinity of the Riemann sum. Riemann sum is k equal to 1 through n f of xk times delta x, which is equal to limit as n approaches to infinity. This one, the Riemann sum, we have already calculated this Riemann sum. We have calculated from here all the way up to here, and we got 1 plus 1 over n. So that is 1 plus 1 over n. And we need to evaluate this limit. So when n approaches to infinity, the limit of 1, the limit of the constant is just that constant, 1. And then plus, when n approaches to infinity, 1 over n. 1 divided by very, very large quantity. So that will be approximately 0. So we end up getting 1. So meaning of that is the value of this definite integral from 0 up to 1 is a 1. So this is how we can use Riemann sum to find the exact value of the definite integral. So here we get the exact value because we use the limit of the Riemann sum. In the previous example, we just find the Riemann sum, the midpoint Riemann sum with large value of n. So that value of the integral will be approximate. But if we choose n as really large quantity where n goes to infinity and take the limit of that Riemann sum, we get the exact value of the definite integral. So this process is called the numerical method of computing the definite integral. And for that, we use Riemann sum here. Okay, that's all in this video. I hope you find this video helpful. Thank you so much for watching.